Hello, everyone. My name is Luke Wilson, and I'm here today with my teammates Michael Marcello, Wilmer Chinchilla, and Daniel Kennedy. Together, we make up Team General Dynamics Electric Boat, commercial off-the-shelf design of a digital and analog in-and-out acquisition system. Our technical directors are Adam White from the URI class of 2014, Art Viola from the URI class of 1984, Nicholas Rommel from the URI class of 2017, and Anna Skelly from the URI class of 2021 from just this year. Many of you know, GDEB has a distinguished history, tracing its roots to February 7th, 1899, when the company was established to complete a vessel that would revolutionize naval warfare. Named Holland for its inventor, the visionary Irishman John Philip Holland, the 54-foot vessel in 1900 became the first commissioned U.S. Navy submarine. Today, Electric Boat is a design yard and prime contractor for the Virginia-class submarine program, and is currently engaged in the development of the Ohio replacement, a third-generation ballistic missile submarine, also called Columbia, which represents the future of the company. EB also supports several other classes of submarines, such as the Seawolf. The motivation behind our team's project. The truth is our project has evolved significantly since the beginning of the semester. While the initial motivation behind this project was to investigate potential commercial off-the-shelf technologies with which the antiquated Versa module Europa bus module, which you can see on the screen now, could be replaced, we are now investigating the viability of an off-the-shelf design of an embedded system. It has become project-driven, quite literally, as you'll see by the desires of the students who have been inspired by the concept of a self-driving car through sensor research. While deciding that such a design will be too complex for the time given, you can see that our sensor system will emulate that of a self-driving car. Commercial off-the-shelf technologies which can be applied in various capacities. Realistically, our project has a higher degree of customization compared to a strictly off-the-shelf endeavor. This provides us more flexibility, as a completely off-the-shelf configuration would be difficult to modify. An example of this is our time-of-flight sensor. While purchasable with full functionality and a paired evaluation board, we found that we could save significant funding by purchasing the sensor and the board separately. The only complication is the need for a sensor PCB, but the cost of that is relatively minor. The anticipated best outcome is relatively straightforward. It is the successful design of a mobile data acquisition solution capable of receiving and storing sensor data that matches design specifications over a wireless connection utilizing several digital and analog in-and-out acquisition units. Quickly, you can see what each of us tackled this semester. Mike, our sole computer engineer, was our software lead. Wilmer researched the system we needed to build and was the designer of one of 3 PCBs. Daniel acted as our PCB design lead, and I was our RC car specialist and led the team in sensor applications. So far, the team has achieved some satisfactory results this semester, which, while I'm proud of them, I'll allow for each designer to go more in depth about each at a later time. That brings me to what I've accomplished this semester. Highlighted on the screen, you can see that my focus was primarily the front of the vehicle, which contains our time-of-flight sensor, but I'm not going to get into that until a little later. Due to an initial objective being to investigate alternatives to the Raspberry Pi 4 and Intel Nook from last year, I investigated the UDO Bolt and the NVIDIA Jetson Nano. However, the Bolt proved too expensive, and the Nano, despite strong machine learning capabilities, which were appealing at that time, they both still do not exceed the capabilities of existing hardware. When Mike presented the AFBR time-of-flight sensor as a cheaper LiDAR alternative, my further research resulted in the discovery of an existing API that would simplify the software side of things. This is made possible through the use of the FRDM Evaluation Board's microcontroller. Therefore, I've designed the PCB schematic into which the time-of-flight sensor will be inserted so that the 2 boards can be joined via header pins. It accepts 2 different voltages of 3.6 and 5 volts and will be at the front of the vehicle to determine where objects are in front of it. Additionally, I poured my efforts into some of the mechanical engineering work that quickly became a necessity for this project. Due to potentially rugged environments, the sensors must be mounted securely. With this in mind, I've modeled the RC car chassis, as most of my efforts were focused on modeling where most of the sensors will be placed on the chassis, as at the time of modeling, the team had limited access to hardware and limited space to utilize on the RC car itself. Therefore, this process is essential to visualizing the system that the team will be implementing next spring. Here you can see a brief summary of the individual work that I've done this semester. What will I look to accomplish next spring? As I mentioned a few moments ago, I intend to have the design of the mountable containers complete within the first few weeks. Additionally, as the PCB board for the time-of-flight sensor will not be complete for several weeks, I will implement a makeshift circuit that will be able to interface with the evaluation board early on so that Mike Marcello will be able to begin his testing. Other goals include continued detailed documentation of the system and some customizations of the RC car, such as swapping out the springs for sturdier alternatives to ensure better measurements down the line. Now I will hand off things to Mike, who will explain some of the computer engineering challenges he encountered this semester.
Thank you, Luke. This is designer Michael Marcello, and I will be talking about the concepts that I have developed and produced over the fall semester as the sole CPE designer. Specifically, I helped to design the conception and initiation of our RC car project for the consumer off-the-shelf design that Electric Boat had requested. I also helped to research different sensors and sensor application methods for the said project. I also performed some informal trade studies on various hardware components such as the Intel NUC, the Raspberry Pi, and the Arduino to see their compatibility with accepting sensor inputs and outputs. I also did research on sensor communications. For example, I did research on the standards of UART, I2C, SPI, and CAN bus to determine their viability with the aforementioned hardware components. I also helped to design various Python programs that aid in the communication of data and the processing of information between sensors and our RC car system. The image presents a great visual representation of what our future goal would be for our GUI. For example, it hosts a multitude of features such as a G-force meter, various voltage and current readouts, as well as some warnings for the RC car system such as low battery voltage, high battery temperature, or other such hazards that would prevent the proper operation of the RC car system. For a physical application of the theory that we have presented, we have idealized a testbed setup, which uses commercial off-the-shelf parts that we have researched. For example, we have our Raspberry Pi, which acts as a communications between our Intel NUC as well as our various sensors. These will communicate via a wireless access point so that our RC car can wirelessly communicate with our stationary Intel NUC. This test bench setup allows us to investigate various technological applications of various practices to demonstrate the flexibility and capability of our RC car system. Our next presenter will be Wilmer Chinchilla, and he will go over his individual technical contributions for this semester. And last but not least, we have Exhibit 3, which exhibits the multiprocessing segment of the project, which demonstrates the progress made in coding expertise and practice. Now, multiprocessing in Python allows for independent programs to communicate with a main executable. This allows for flexibility as well as expandability within a given system. The structure of this system allows us to pass data to the main executable using queues. The main goal of the multiprocessing function in Python is to decrease GUI latency, so that the user experiences less delay when applying certain actions. Our next presenter will be Wilmer Chinchilla, and he will go over his individual technical contributions for this semester.
Alright, coming up next is my individual contributions. So first and foremost, as everyone else is aware, we had to delegate the research for this specific project, and since it's a given input and output sensor system, we needed a lot of research given on the sensors. Now, I am by no means the only person who did research, but I did also contribute. This includes looking into the accelerometer, the gyroscope, as well as many of the others, such as the photoresistors. But besides those sensors, we also wanted to make sure that they had a given purpose within the system, within the RC car. So we had to look into how they would function and how they would work with the robot. So for instance, with the photoresistor, obviously, it would indicate or it would pick up the light from either outside or inside, and then it would turn on the headlights as a result, or it would simply notify you. And there's also the gyroscope. We needed to make sure that was on there to actually tell if the car is upright or not in the event that we cannot see it. The accelerometer is, obviously to indicate where exactly it's going. So it measures the velocity, and the temperature sensor to make sure that the battery isn't overheating or that the system itself is within expected range. Now, while these things are all nice and dandy and we can measure them, we have to make sure that they have a purpose. And so obviously some of them are more obvious than others in that the temperature sensor is to help with the overall lifespan and longevity of the system, since we don't want any overheating. But also the things like measuring the velocity and all the forces on the system itself is useful in collecting data and whatnot. And especially if you're setting this thing out and you're not able to see it with your own eyes. It's useful to see, kind of treating it like a rover in that, you're able to pick things up and search through the environment. Now, next up would of course be finding out the specs of all these sensors, and there's a detailed Google spreadsheet detailing the prices, the functions, what power, how much power it requires, and how much it outputs. But I also did contribute in that. I did want to specify that I was in charge of the design and the visual aids, especially the big one that everyone has seen. I am by no means a graphic designer, nor is it my passion, but it is something that I feel like could help contribute to the team. And lastly, the most recent contribution that I've made is the main PCB, in that it kind of has the it's like a main hub for the system, in that it holds the gyro and the GPS, which kind of have to be into the center of the system to kind of get the proper readings that we need, but also has a direct connection to the Raspberry Pi, which is the brain of the system. And right here, like I said, this is the main graphic that we're using, detailing how everything is laid out, how the whole system connects and speaks to each other, whether hardwired or wireless. Then moving on.
Hello, my name is Daniel Ganabi, and I'll be going over the individual technical contributions. Contributed to the SDD rough draft, wrote a paragraph on the sensors and what their functions were, collaborated on the finalized list of sensors with Wilmer. Mike and Luke pitched in a little bit on that, and we all came together to source the parts for the sensors, develop slides for the project risks, sourced batteries and battery monitoring devices, PCB design for the power converter, sourced the parts for the power converter, and help the other designers get familiar with Ultim Circuit Maker 2.0, as I was the only one taking the PCB course. Okay, here's the schematic for the power converter, which we got at Webench. We're expecting a 9.6 input voltage from the battery, which goes straight to the Texas Instrument device, which acts as our converter, sends out the voltage signals through the inductor. The inductor cleans out the voltage signals down to the voltage divider, which outputs a fixed fraction of 9.6 volts to 5 volts here, as you can see. At the bottom here, we have a USB port type A, which goes to the Raspberry Pi. Okay, this was the remaining technical challenges we had for this project. The design of the GUI, utilization of GUI to display system data. Mike was responsible for this. He did make some progress, but I don't think he's quite finished with that yet. 3D printing sensor mounting hardware, fabricating and testing PCBs, integrating hardware and software components, and verifying system design document requirements. Our risks are as follows: the budget, resurgence of COVID-19, shipping and supply chain issues, and finally limited CPE personnel, with Mike being the only computer engineer. Okay, and that's pretty much it. We would like to thank Dr. Sunak for his guidance and directions setting up this program and reminding us the importance of passion and urgency. We have Art and Adam, technical directors, who have been with us every Friday, who have been helping us and guiding us through this project, and Nicholas, who pitch in when they can as well. The university, Mary Leach for guidance with RC car application, John Lemmy for instructions on Python multiprocessing.